Hey, welcome back. Thanks for coming. Michael, could you push the door shut, please? Thank you. Those of you who submitted homework, you got your feedback today. If I didn't give you feedback on your homework, it's because I didn't file it correctly and send me an email. And you'll note the feedback was very brief because I said if you tried, you got all the points. But if you want to learn more, if you want to talk more, just come talk to me about the assignment. And I can help you more. Or if you want to try to redo things or something like that, that you know you might have not done, we can talk about it. But it's more just, I'm wary that you have something due this week and something due the next week. And it's like, I don't want to, I don't know, it's just too much. So.
Can I ask a question?
Yeah.
If there were things in that homework that we knew weren't right in our model, like with the R code for specific reasons, is that going to affect how we do it in this next homework? I haven't even looked at the next one.
No, the next one is going to be...
So it's unrelated.
Yeah, so homework 6 is all the measurement and variance stuff, which is due Friday. Homework 7, I guess I say due. Everybody can have till the 15th to do it. Homework 7 is due the 15th. And that's the SEM project, and it can be.
So homework 7 has no connection to homework 5.
That's right. You don't have to do so you don't have to do the categorical data analysis in homework 7, and for your data, it's probably better not to.
Yeah, that's where mine.
Yeah, you and Shada had the same issue with that, and so but the homework 7, there's multiple options on what you can choose to do. It's just mainly do some type of structural equation model, whether that's a multigroup or a higher order factor or an actual path model with the latent variables themselves. Okay. What do you remember from last time? Path analysis. Mediation and moderation. Ugh. Does everybody love mediation? No, this class hates mediation. That's right. No, nobody hates it. You love it? Oh, okay. You're on the train, huh? That's awesome. It's a train that kind of has a circular path. No, not quite a circular path, but you know, it's over here. So I realized that Excel left off at slide 13. So this is where we were at before. We were discussing the finer points of mediation and moderation briefly. Do you have any questions about this for what we talked about at the end of class? I know we talked about how. Oh, I was going to show you how moderation, how the interaction affects the main effects. Is that right? Okay.
You said that we would talk more about like in the previous class sorry. We have been told that don't interpret the main effect.
Don't detect. That's right. Yeah, let's do this. Okay, let's imagine that we have a model where moderation is happening. Moderation is an interesting word, isn't it? If you didn't hear it in statistics, what would you think of it as? Discussion? I always think of drinking. But then again, that probably means I always think of drinking. But everything in moderation except for thinking about drinking. But anyway, that's where I hear it from. But I've also heard it in so it's cold today. I'm a weather geek, by the way. I love data and whatnot, and weather is part of that. So it got cold, and the air is coming from kind of a little bit of the Arctic. It's Canadian air. It's not exactly Arctic. But there's no snow, not much snow north of here up until the Canadian border. And what happens when the air pushes down is, it's rolling over land that's not that cold, relatively speaking. And so it starts to change its temperature, and it moderates. Have you heard that also? So moderation is a way of, the word that we use it for, and the way we talk of the word moderation is something to think of a change. Somehow modifies or gets a modification, really, of what happens, which I know it's another term that we use. So let's imagine we have an outcome y, and just to be consistent, y, m, and x, right? So m and x are it. So y is equal to, and I'm going to leave the subscripts off of the y and m and x, but y equals beta 0 plus beta 1 x plus beta 2 m plus beta 3 xm. And now m can be quantitative, it can be dummy code, it can be whatever. But here's what happens. When you have an interaction in the model, when it's present in the model, what it's going to do is it's going to change the main effects. So let's talk about what the main effects happen to be. Beta 1 is the main effect of x. But note, because x is right here, right? Whenever you plug in a value for m, like if m was 1, now you've got a beta 3 multiplying x, right? So if you're talking about main effect or slope, right, it's something multiplying the variable x. And if you have x showing up in multiple parts of the model, there's going to be something potentially multiplying it. And in an interaction, that's what's happening. So what's happening is this is the main effect of x, or slope of x, when m equals 0. Because when m equals 0, this part of the term, the interaction term, goes to 0. Right? So this is what's sometimes called a simple slope, which is what Jihong said before. I've also heard it called a conditional main effect. That's the one I prefer. Conditional main effect. And that's because the main effects are truly conditional on the interaction term when interaction is above what you have. Michael hopefully remembers this from multivariate, and those of you who haven't taken my multivariate, and that first homework made everybody cry, but this is about. I don't want to make people cry next time, but I do think it was a very good drill on interactions. How many of you have seen this before? Michael has, Jihong has, and the rest of you. So this is what multivariate was supposed to be. Skorupski. Anyway, sorry. No. So when we do this, by the way, this is sort of my one of the things that we don't do well, in my opinion, is we don't teach that regression ANOVA multivariate sequence well.
Yeah.
And which is a shame because there's so much time spent on it.
Yes.
And one of my goals is to revamp it. And so that's why I teach multivariate. I try to teach multivariate each year, but last year I didn't because I had a buyout and a course release, and so I thought this is my chance to get things taken care of and whatnot. And now you suffered because of it. So I'm trying to think of a way to make it better and whatnot. But this is motivating me to want to teach like the 810 class. What we're thinking of it as is 810's regression, and then 905 is multivariate. And if I could teach both of them in sequence, then I could give you this. And then you could go into the bigger classes and be like, I don't understand an interaction. Because ultimately, it's really hard to learn SEM, but you really need to know interactions as well as you do it, right? And so the interactions are more fundamental. So anyway, this is not your fault. So do you see why, though, this is not, beta 1 is the conditional main effect? Let's talk about what really happens to the main effect. If you're talking about the slope of x, you have to take, if you really want what the slope happens to be, right? What the slope of x happens to be, right? You have to take beta 1, which multiplies x, and you have to add to it beta 3 times m. Oops. Right? So in that case, the real slope of what's happening to x is this right here. That's what happens to the slope or the main effect when you have an interaction present, because x is part of this, and if you're really thinking what x is, it's this. Right? It's like algebra, if you want to talk about it, kind of combining like terms. This right here, beta 1 plus beta 3m, is that. Yeah. Ahmed.
Don't we multiply like that to get the...
You would if you were talking about mediation up here, yes, but we're going to be in this situation with moderation right here, where really x and m is a product. And so because of that, there's no path weight here, but it's causing, because x and m show up in the model, it's causing the path to be modified by it.
So in the first,
In this?
what I'm trying to digest is the idea that we have regression, like we have sub-regression under regression, like because we have you understand what I mean? Like, like, but when you said that bad analysis is multiplying the I'm sorry.
No problem, no problem. Just think it over real quick. Let me try this real quick. So for moderation, it's all about interactions. Same thing works. So this is the slope of x. What's the slope of, so the slope of x, what's the slope of m? Slope of m is also, it's now the coefficient that multiplies m, beta 2, plus what modifies it, which is the interaction, beta 3 times x. Right? That's really what's happening. Here's the slope. Right? So what you see in a regression analysis or an ANOVA when you have an interaction term is not that you ignore the main effects. It's that you have to talk about them conditional on the values of the other variables. And so what you'll end up seeing is a graph that looks something like this. You may have, this might just be beta 1 right here, but what you might see if you're trying to predict, remember, this is the conditional main effect of x. That's when m equals 0, right? But when m equals 1, you might see the slope looks like this. And when m equals negative 1, it might look like this. So what you end up getting are 3 different types of plots, and I don't know that I've actually done this well because they may need the same intercept. But you may end up getting 3 different lines. Imagine the intercepts right here. There we go. That makes it work. So what you'll talk about, this type of analysis is sometimes called simple slopes analysis, where you're looking at kind of, or regions of significance is really what I'm talking about. You want to know, is the main effect of x significantly different from 0? Well, in some range it will be. Right? For some range of m, this slope right here in the middle, you can tell when m equals 0, the slope is not significant. But somewhere around here to here, so this is the area where it's not significant. But maybe above, m of 0.5 and below m of negative 0.5, you might find significance for that slope. Right? So this is what happens. So what you're really doing with this model is not ignoring the main effects. It's really you're having to describe them conditional on the interaction as well. So does that help maybe?
Yeah, it's like what I'm trying to, maybe my way of trying to understand is incorrect, but we have like the regression equation, we have the intercept, and the value of the intercept would be, I don't know how much the value, but it would be that value when the other variables, other predictors
are zero. That's right.
So we are talking about the same logic here.
That's exactly it, yes. Because the main effects modify the intercept. The two-way interaction modifies the main effects. If you have a three-way interaction in your model, guess what it modifies?
So there is variances associated.
The two-way interaction. And the two-way interaction then modifies the main effects.
So how you partial out the error associated with like like when you the slope, the first slope, the second slope, is there an associated error? So like for the slope of x.
Slope. No. This slope has an error. Each of these has a standard error. But then when you go and combine them like this, yes, there is an error that goes with it. And the way you find that error comes from the linear. These are effectively what we call a linear combination of variables. And so if you remember, we briefly touched on this before. When we talk about, I don't know if we talked a whole lot about it, but if we take one random variable and add it to another, creating a brand new one, the mean is the sum of those two. The variance, though, is the variance of 1 plus the variance of 2 plus 2 times the covariance. We did talk about this in classical test theory. Well, the same thing happens for this right here. If you wanted to know what the standard error of a slope might be at a conditional on a value of m, you have to do the same thing. You have to know the covariance between the two slopes. And in your software package, it has it because it's built in for the most part. Not all of them do, but somewhere in them, for most linear models, it's the variance covariance matrix is part of what happens to in the estimation process. So so yeah, it's something that yes, you'd have to get effectively a standard error for this. The standard error is a function of m as well, and it you'll be able to see this.
Is it possible that for the standard error, like the linearly combined standard error for both predictors would be less than each predictor standard error?
It is possible. It depends on.
I'm not talking about possibility. I'm talking about theoretically speaking.
Theoretically, yeah. No, I wouldn't say it should be. It could be. All right, and again, think of it this way: if you have the m of 1, then the sum of beta 1 and beta 3 gives you a variance of the variance of beta 1 plus the variance of beta 3 plus 2 times the covariance. And the way it can be smaller than is if the 2 times the covariance, if the covariance is negative, right? You start to get it shrunken. Now, I may be wrong about that. There's the equation parsing it, but yeah, it can happen. Yes, it can. So, okay. So, mediation, moderation. If you want to know more about the main effects, the interactions, and the linear models and regression and stuff, on my website, in my multivariate section of my courses, go to the last time I taught it, and I have my lecture slides and my video from when Michael was in 905. And there's 2 or 3 lectures at the very beginning of class that deal with specifically that. So I'd point you there. I wish I could give you more time on it here, but let's just move on. So for mediation effects, bless you. So if you were to look at here, this is sort of what we're talking about. In that triangle that we saw before, A, B, and X predicts M and M predicts Y, and X predicts Y, what we're looking at here, if we were to label these, if we just predicted X with Y, that would be the direct effects of X and Y. The big question in mediation is the effect of the direct effect, or C, still significant after we control for M, right? So another way of putting it is, does this C value equal this C value if you were to do the 2 different models? So the old rules, I don't know, there's a lot of old rules with mediation. Some of them are a little too strict. I don't know, we need to talk about that. The big issue that we talk about in here, let's just go over into the example. Let's do this. In example 9a, this is what you see here. And example 9a, let me see, do I have it? This is an example from Lisa Hoffman's dissertation. Actually, we have it coming up here. This one right here. This is the example. This is the path. Come on, Temple. This is the path diagram. There we go. This is not her dissertation. This is actually from a study she did with a colleague up at Nebraska. So let's imagine we have an X predictor here, which is a mindfulness of a subject, and Y, which is warmth towards feminists, and we have a bunch of mediators. The research question are, to what extent do these 4 mediators account for the relationship between mindfulness and warmth toward feminists? And 2, how do these direct and indirect effects differ by gender? Well, to talk about that, let's take a look at this. Mindfulness has a direct effect on your feelings toward people who identify as feminists. The mediators are internal motivation to respond without sexism, external motivation to respond without sexism, hostile sexism, and benevolent sexism. I don't know what each of those are. They sound bad. So let's just go with that, right? So what we can do with this model to build this, it's how we turn a statistics class into something that makes me really nervous, because I'm not used to talking about, cultural or gender or religious issues in class, because it's not the type of statistics are very benign for the most part. Right? I'm offended by statistics, but I'm a rare case. Statistics rarely offend people. It just usually bore them. When I start talking about this, I could feel the anxiety just ratchet up a level here, right? So I don't know what this is about, but let's talk about mediation here. The model itself, if we wanted to talk about this, we have a y variable here. Oh my goodness, I just completely... Yes, there it is. The y variable is, in this case, it's non-traditional predictors. So here, where I put in all the model here, this is the single group model. You have all of the predictor variables here. And this is, we're labeling every term. We're labeling all the intercepts and the residual variances. Then we're also labeling this right here, each of these 4 variables, intern, extern, hostile, and benev, those are the 4 mediators that we saw. Oh, not that way. Where'd it go? This way, right here. Those are the 4 mediators. 1, 2, 3, 4, right? So we have a regression where we have mindfulness, mind 1c, which is a centered variable of mindfulness, predicting each of those. And remember in Levon-Ease, this is... this thing in parentheses times that is trying to capture its slope, put a label on it. Because what we really want to do with that slope is to use it to form our direct and indirect effects. That is the direct effect of mindfulness on each of those 4 mediators. But we're going to need it to make our indirect effect predicting non-traditional beliefs is what I have on as the variable here.
Could you zoom in a little bit on that?
Yes, I am sorry. Thank you for asking. Is that better, or would you like it more? Okay. Sorry about that. In my anxiety about the topic, I'm forgetting. Sorry, I'm trying to make fun of myself here. I hope it comes through. I am far from perfect these days. It's funny how as you get older, you think I get better at stuff, and I just realize how much worse I was. It's like
But looking
when I was
at
young and
people's
brilliant.
our outputs, I learned that like it can be kind of long.
Yes.
But it's okay to keep the word so that you understand what you're talking about.
Absolutely.
Because when I started, I made it too short, or just like I had to go back to reference so many times and just took a long time. But this is so nice and neat.
Yeah, I will tell you the thing about the coding for R with me, what I've learned to do on it is to try to, there's no limit to how long like variable names can be. So I'm notorious for how long I make them because I want to know what's in them. Whereas M+, which is, I adapted this example from Lisa's work in M+. M+ limits the variable names to 9 characters. And so to try to keep the variable names consistent, you see these are somewhat shortened, but I'm trying to be verbose in the syntax so that you can see all the parts that are moving around. You'll note also, so this was the left-hand side of the model. Now, to predict Y, which is, in the graph that I showed you, warmth toward feminism over here, but here it's called non-trad.
So just before when you say the left side of the model, we are trying to predict now can I go back to the syntax?
Yeah, hang on. This is the left side right here. And oops. Oh, come on. There we go. So because there are 4 boxes there are 4 equations that represent the prediction of each of those mediators by x. Here, mind 1c is x.
Is mind x. So you want to predict that by x.
Yes, that's right. So each of these is predicting each of the 4 mediators. Now, on the right-hand side of the model, that's the part that deals with the outcome, final outcome. We have one regression line, and we put all of the predictors in. Here now we have the x variable, mind 1c, but then the 4 mediators as well. And again, each of those has a label in front of it. Now, this model, couple parts. You note in here, there's no equal tilde. Right? Why is that? All observed variables in this model. Doesn't have to be. In fact, we can swap out this, and we probably should have swapped this out. These are all scale values. These are all sum scores, effectively. All right, so if we were to do this as a structural equation model, which will be the culminating example in class this year, next time, what we would see here is that we would define our measurement model at the top, like we normally would with an equal tilde. And then the name of the variable for that measurement model now takes the place of these variables down here. So this part of it is regression, but it works the same that you would do when we get the latent variables in as well. So if you remember the terminology of path analysis and structural equation model with the idea of what's an endogenous versus an exogenous variable, how many exogenous variables are here? One. Very good. Only one is mindfulness here. And so the rest are endogenous, and that's again because they have a terminating arrow predicting each of them. And if you look, kind of as a guide, for every endogenous variable in your model, it'll be on the left-hand side of a tilde in the analysis itself, because it's being predicted. All right, and I mean by tilde, I don't mean like tilde 1 defining the intercept. I mean tilde defining the regression line itself. So the way we form indirect effects, and this is where if I flip back to Excel here, remember that the indirect effect of a variable is the slope for x multiplying m times the slope for the slope for x predicting m times the slope for m predicting y. And the way you can think about that is A, the slope of x predicting m, is the amount of change in m per 1 unit increase in x. B is the amount of change in y per 1 unit increase in m. So if you're talking about how much does if x goes up 1, how much does y go up indirectly? Well, x goes up 1, m goes up a units. And if m goes up a units, y goes up b. So a times b is really what happens. So what we're after here is the product of those two slopes. And so that means in Lavon, what we can do is create using the the colon equal function. Remember, colon equal was where we define a new variable. We define how it's built. That colon equal function takes the product of those two slopes. And here, when I highlight it, you can see where they come from. All right, this is x to m1 to y, which is the pathway that goes right here. This one and this one right here, x to m1 to y. That comes from the prediction of internalizing by mind1c, multiplying the prediction of non-traditional by internalizing. And that gives us the effect. And so we have all four of those there. And now we look at our analysis. By the way, we can look at model fit information first. Turns out this model has 0 degrees of freedom. What does that mean? Saturated. Just identified. So model fit should be perfect, which is okay. All right? I don't have as much of an issue when you have this this model. But
as much.
Well, there's still the philosophical issue that this model, you can change the arrows of the paths, right? And you'll end up with different results. Or you could say everything's just correlated with each other and there'll be another different result. So that it's still interchangeable with other models. So it's not necessarily testable, but it, for whatever reason, doesn't offend me as much as if you have a measurement model and you have 3 indicators. There are 3 variables for the measurement and it perfectly fits. So either way, it should be 6 of one, half dozen the other. But I'm just not going to. Let's just describe it rather than get into the nuance of it. So what you see down here, you have all the estimates. For every one of the predicted variables, if you ask for R², you'll find it, right? So it's another way of figuring out what's being predicted. I'm telling you this because as you're running your model, you have this effectively maybe a diagram in your head or some type of, conceptual model as to what you want to try to test. Just double checking that the variables that are being predicted in your conceptual model are really showing up in R² is a good place to start. And you note here that X is not predicting any of the R² for each of the mediators is very small, right? which is indicative that there's a zero, effectively a zero path for most of them, it looks like, right, or very small path. So let's take a look at the defined parameters, though. These are the indirect effects. So x to m1 to y gives us a regression slope of 0.188, unstandardized. Turns out that has a very small p-value, so we might say it's a significant indirect effect, or that the mediator M1, which is internal motivation to respond without sexism, provides an indirect effect between mindfulness and warmth toward feminists. So evidently, if you're more mindful, it means you're more likely to be aware of your internal motivation to respond without sexism, which means you're more likely to be more warm towards feminists. So for every, what does this mean? For every 1 unit X goes up on mindfulness, the Y variable, warmth toward feminists, goes up 0.188 units itself. Now, that's indirect. If we were to talk about the direct effect of mindfulness on the warmth for feminists, you'll see the direct effect is negligible, right? The direct effect of X predicting Y has a p-value of 0.966, which is pretty much close to zero, right? So it's telling you that mindfulness itself does not have a direct relationship with warmth toward feminists. It's really an indirect relationship that it has. Moreover, there is something called the total effect, which I don't describe in these slides, but it's something that sometimes shows up. The total effect talks about how much the outcome variable y changes when x goes up both directly, or sorry, how much y changes total, which means the sum of the direct effect plus all of the indirect effects. All right, so for every 1 unit of x, if you go back to this plot, for every 1 unit increase in mindfulness, you get negative 0.009, y decreases by negative 0.009, that's a 9 there, directly. But then each of these indirect effects also contributes. And the way you find the total effect, I didn't put it in here, but I'm going to put it in right now. It's a sum. It's a sum of the direct effect plus each of the indirect effects. Yeah.
About what test of indirect effect. Because indirect effect is A multiplied B, could it be used as what test to test the effect?
Let me get to that in just a moment. The short answer is no, or probably not. The longer answer takes a little bit more of a description, though. Oh, I don't want C with a little French mark on it, or other mark on it. Copy and paste template. Come on. I'm trying to show you the total effect. Let me just describe this real quick. Yeah, no, plus right here. And we want then the x to y path as well. Right, so we're summing all the indirects together. We're doing all that. We push play, and we look at the output. And so now what we end up seeing is this. As x goes up 1 unit, the total increase in y is 0.351 units. But that total increase is actually not significant either. And that's because, again, x does not predict y directly, as we saw right here. And x does predict mindfulness directly, or I'm sorry, x does predict internal motivation to respond, which is M1. It also predicts hostile sexism. So as you're more mindful, you're less likely to be, your hostile sexism goes down. All right, so that's why those two paths are significant. But then overall, it's not enough to make it so where that x has a direct or indirect, a total effect on y much at all. Mindfulness doesn't seem to matter as much, totally. But the indirect effect does matter, which is an interesting phenomenon. You can have this happen, this kind of cancelization process happen. That's some reasons why you don't talk about total. Now, back to Jihan's question. There's an issue. Come on. There. There it goes. I have no patience anymore. I gotta calm down. Anyway, I need to be more mindful. Let me just take a deep breath. No, I don't mean that as a joke. I need to like chill a little bit. The big issue with the mediation is that you have the product of these coefficients. How do you form? What happens with the product of the coefficients is that if you have two things, if you have one coefficient A and one coefficient of B that as n goes to infinity should have normal distributions, then the product of them shouldn't be normal, right? In fact, it should be, unless, I mean, there is a way where, no, that's not even true. The product of them can't be normal very easily unless n is super big. So what people end up doing is the following. They bootstrap the data. And this is where I needed to do my homework in Lavon, and I tend to have forgotten. You can do I want to say that M+ does it automatically. I don't know that Bootstrap works in Lavon right now for it, although there is a Bootstrap Lavon function that you can do to do this. I believe what you can set is Bootstrap. SE equals Bootstrap. So what I should have done to make this work better is in my Lavon syntax, I should have put another comment right here that says SE equals, and if I do that, I'll by the way, I'll re-put this up on the internets. Oh wait, ML estimator. I have to use ML for that. Okay, got it. Yes, sir. So now it's taking a while longer. It's taking a while longer because what's happening is what people have done to shortcut that non-normality of data is what they do. They take resample. Does everybody know what a bootstrap is? Does anyone not know? So I'll just describe it briefly. A bootstrap process is where you take your data set and you get your initial estimates of the parameters, and then what you do is you take repeated samples from the same data set with replacement of the same size. So you create a bunch of brand new data sets, sampling from your data as if they were the population of people that could possibly show up. And then they re-estimate the model for every one of those sampled data sets. And they get a distribution, or a kind of a distribution of each of the parameters in your model. And that bootstrap, what it ends up doing is giving you a little bit better, I would say more accurate version of standard errors, because the standard errors that come from that distribution of what the parameters should be reflect a little bit more of reality for the data and a little bit less of the assumption of normality or all the other things that go into it. We only had 999 bootstrap draws. This is one of the other problems that happens in bootstrapping, is that not all of them may converge. And I think it looks like, I'm guessing there is 1,000 bootstrap draws is the version that ends up giving you the values. And what you'll see here is the p-values, I think, are roughly equal to what we saw before. A lot of times the bootstrap result and the non-bootstrap result do agree. Not always, though. It's particularly in smaller samples. So big picture is to do mediation and to do it where people won't complain, you'll want to put this SE equals bootstrap in. And I apologize to you for not putting that in ahead of time. That was something on my list of things to do, then just went by the wayside. I'm sorry. Yes?
Why do we need to use vector analysis? Just
for the mediation is where it seems like for a lot of publication these days goes. You can use it for anything. You can use Bootstrap for all sorts of reasons. It's sort of an empirical way of getting a sampling distribution of your parameters.
So what mainly for the standard error? The
standard error, yes. The standard error of the coefficients depends on the model assumptions. And it depends on how much data you have. Right? Basically, in the ML result, the bigger the data, the more, as n goes to infinity, the more likely you are to have the p-value look accurate, the standard error look accurate. So the Bootstrap tries to shortcut that itself. But So, other questions or thoughts? Okay. Well, you can do mediation with all sorts of stuff. The other thing you can do is a multiple group model with mediation. Remember the multi-group? Does this model sorry. Remember how tedious it was going, that's what that was. Oh my goodness. Remember how many, right? Well, we can just do that. Here, we didn't go and test for different, we just wanted to put male versus female into the model and not necessarily go through, because these are all observed variables in theory, although they're not necessarily. Let's pretend they're observed without error or whatever else, like someone's height, someone's weight. There shouldn't be, you should expect them to be somewhat non-invariant across gender or groups or whatever you're looking for. But again, we could do multi-group. Again, here you see this, the syntax where we have the two groups labels in front of each of the parameters. The parameter, the syntax is mostly the same. The only thing that's different is I have an F in front of the X to each of the labels for female, and I have an M for in front of each of the labels for male. Mm-hmm. And then I go and create indirect effects for female. I create indirect effects for male. But then to test differences in the indirect effects, I take differences in the direct effect paths. Right here, I can create the difference in the male and female parameters by taking the label and putting a minus sign between them. Mm-hmm. Now, to do this accurately, I would want to put in the Bootstrap SE, but that takes a little bit more time than I want to show you right here, so I'll do that later and put it up online. But to show you what the results happen to be, again here, this is again a saturated model, so we don't have model fit to worry about. But now we can go look at each of the groups' results. So here are the results for the female group. Right here, you see the R squared for each of the variables. Here's the results for the male group. Right there. And let's see if we can define some of these parameters. Here, this is the indirect effects of X through M, the first mediator. In the female group, you see here are the here are the four indirect effects. Depending on how you interpret 0.065 as a p-value, you might say that all four of these are non-significant. Right? There's no significant indirect effect between mindfulness and warmth toward feminists in the female group, whereas in the male group, there is the first one, which is internal motivation to respond without sexism, is an indirect effect that is significant. And if you want to talk about differences in the regression slopes for each of these, this is each of the side of the regression slope, you'd see here that the first, for X predicting each of the mediators, there's a significant difference for M1, a significant difference for M4, and maybe a significant difference for M2. But there's no difference for the mediators predicting Y. So where the differences in the indirect effects are coming from really is coming from that first part of the equation itself. Right here, it seems like men and women differ in the relationship between mindfulness and each of the mediators more than they differ on in the relationship between mediators and Y. Shada.
Perhaps it's what I pulled up, but in that example, it only goes down to RMSEA. It's like the last.
Oh no!
So if you don't see all those parameters, and then if there is another.
I will repost it. I'm sorry.
No, that's okay. I just wanted to make sure it wasn't me.
No, it's not you. It's usually me. I know myself well enough to know, yeah, I screwed that up. There, okay. Sorry. Again, gosh, here we go again. Falling apart, template, bring it back together. Okay, so really what you'd want to do with this analysis, and I'll do that for the online fix, is to put this through with the SE equals Bootstrap and change the estimator to ML. I'll push play on this, but it might take a while to actually do its work. Jihan.
I'm thinking about the multi-group F model.
Mm-hmm.
Can I define a new parameter which use one parameter in male group minus the one in the female group?
Yes. Yes.
Do like a compare test the significance between two groups?
Yeah. Between the parameters of the groups, yes.
Yeah.
Yes. And so that's what you see right here.
Okay.
This is the male group label for the slope from X to M1, and this is the female group version of it. Mm-hmm.
Why we don't do this in measurement environment?
You can.
Okay.
One of the issues, if you do this, so what I taught you with measurement and variance was constraining everything to be equal and look at modification indices.
Mm-hmm.
And then you could think, well, okay, the flip of that is, let's take factor loadings. Which one was that? That was metric invariance, right? Metric invariance, yes. Metric invariance. To test, you went from the configure model to a model where we constrained all factor loadings to be equal, but we freed the factor variance, right? Allowed that to be unequal between the groups. If you think of the configure model, we could have tested for differences in the groups and all the factor loadings, but we couldn't have an analogous model to where we constrained them all to be equal but freed the factor variance. And so because of that, I can't find an easy way. There may be an easy way, a better way to test for it. But the problem is we have to put some constraints on the factor loadings to be able to free the factor variance to be able to test for differences with respect to the items while the variance is allowed to vary. So you could do it. And actually, this is where, when I started with my example for the multi-group, I think it was example 7, I didn't, Levon was giving me weird numbers in the modification indices. This is where I didn't realize you had put, and somehow I stumbled on to putting a couple different options in that didn't seem to be there, and it gave me the modification indices I wanted. But I tried starting exactly the way you thought about, which is I could take differences in all the parameters and check to see if I need to, if it's allowed, but I can't. You can't get the right. They don't. The results don't sync because of that. In the metric model, you're freeing one parameter but restraining the others. So it's this odd combo. Should sync, but doesn't. Other questions? Okay, let's go back to the slides. You can do mediation with non-normal variables, right? You could predict logits or binary or whatever else. There's nothing wrong with that as well. This is an example from Lisa's dissertation. There we go. My dissertation, I profess to you that is incorrect, and you don't want to see it. So, because I did not test for measurement model invariance, and I did build something for structural model without testing for measurement. And you know what's wrong with that, right? Huh? Any differences I found could have been because of measurement model differences, right? Don't be like me. But here, this is an example where she was looking at a driving simulator with elderly adults, where she had some measures of visual impairment, some measures of processing speed, or a measure of processing speed, and then how well they've been as a driver. And she was predicting results on a test that gets used commonly in elderly adults for visual attention, and a test that she created itself called driver scan. And this is where, let's see if I can go back to, let's go with the other one. This we're gonna go, oh, look at that. The result finished. I don't know if this matters or difference with the previous one. I always like to look at those p-values that were close, and they're still pretty close. They're not exactly on one side or the other, really. Although I think, nope, they're all about the same. So. Okay, I'll repost this one. If I pull up now example 9C, this is it. Uh-oh. Oh, come on, man. Of course it's not in there because you didn't put it in there. You're in a different folder. Templin. Sorry. Telling you, the older I get, the better I was. I knew everything when I was younger, especially like right out of grad school. Man, I was good. I don't know what happened to me. You've heard that said before, I'll bet. So this is a model where what she's trying to do is come up with, it's a structural equation model. She's got a path analysis, but she's got latent variables involved in the analysis as well. And so what she's going to build is several measurement models, and then from there she's going to put them together into a big structural model to test for mediation and other effects. So with the first measurement model is for visual impairment, and again you see this is using the equal tilde. So this is a latent variable, right? So this is vision is what we're calling it. It's being predicted by 6 outcomes, and you'll see RMSEA, where are you at? 0.067, CFI 0.976, TLI 0.96. Close enough. Call that good enough. You get into the next analysis, we have driving impairment. This is for actual reports of when you've had accidents or tickets for speeding or failure to maintain lane or whatever else. I don't remember. There's a residual correlation between speed and time, but these are variables that are observed that are interesting, have interesting behavior. But again, the model fit RMSEA 0.67, CFI 0.92, TLI not as good, but let's pretend it's good enough. And then visual attention. Attention is a factor with 3 variables. Dum-dum. But now, you saw that. Remember, this is the sort of the process you go through. Always build your measurement models first, and then build your structural models after that. Measurement models, here, show up first. Now we put it together into a single analysis. We have vision, driving, and attention all together. We have the residual correlation between speed and time that came from the driving measurement model. And then in the structural model, we end up putting in vision is being predicted by age, which is mean-centered at age, or centered by a constant 75. So 75 represents 0. Attention is being predicted by age, 75 in vision. And then log of processing speed is being predicted by age, 75 in vision. So if I go back to this one right here, in her original model, she had done this trick where she put an observed variable into as a latent variable by setting the factor loading to 1 and setting the residual variance to 1. And what this ends up doing is like pushing this thing up as an observed variable. This is a trick that people in structural equation modeling have done for years. I don't understand why it's needed. And whenever I talk to them, they're like, "Well, yeah, I don't know why I need to do that, but I do it." So it's sort of a it seems to be a legacy held over from the original days of SEM, where Lizral would work a certain way, where the structural model all had to be like latent, and they had to trick it to put different things in it. We don't need to do that anymore, so I don't know that that's needed, but maybe you can, if you see it differently, then.
So I have a quick question.
Yeah.
Back to the path analysis.
Yes. Yes.
So then processing speed should be like have an arrow connecting it to age then, is what you're saying.
Yeah, let's see here. Yes, that's right. Here, age and vision are predicting processing speed, so this is not it. Let me see if I can.
Age is interaction plus additive vision, because age 1 times mean-centered age.
No. See, these are labels right here out in front.
Okay,
yeah,
okay.
yeah, yeah. I can see where you say has the redirective effect. Mean-centered. Let me see if I pull up her original example. If I can get a good example back for you. If she has a picture in here, real quick, because I should have plotted this. Does Word take forever to open on your Macs? Yes. Oh, fun. Fun. Okay, here we go. This is the M+ path diagram for it. Right here. I don't think this helps very much, but here is age, right over here. predicting attention, driving ability, processing speed, and vision. So this is how it should look. And again, this is that weird trick of putting the observed variable up into the model using a latent variable. I didn't do that. I just put it directly in the model because I hate having to add extra terms. It drives me nuts. So, and I don't see a reason for it. But then Megan, maybe I'm wrong, but I don't know. So here you have the three regression equations of age on the latent variable vision, attention, and processing speed, the observed variable processing speed. But you'll note, once you define your measurement model, the variables on the left-hand side, the name of the factors, just function as variables later on in the code, right? So it's like you have them in your data set already. So there's really no, like why the SEM part of the class is cut down to like this much is because once you know how to do the regression side and once you know how to do the latent variable side, putting them together is not hard. The hard part is making it work, getting the model to fit. There aren't that many more additional things to worry about when you put them together. All right. So now you see this, we predict this, and then driving is predicted by each of these. She has a residual covariance between processing speed and visual attention. Right here. And so what she's after is the indirect effect of age on vision. So here's age. Oh, sorry, these are the indirect. These are this is the indirect effect. These are on vision on age and vision on driving. This is where we're trying to predict the outcome for driving. Driving ability is really what we're after here. And so she has an indirect effect of age on vision and vision on driving. So that's this path right here, age to vision to driving right here. The indirect effect of age and speed on driving. So that's this effect right here, processing speed that is. So this path times this path. And then the effect of age, the indirect effect of age on attention and attention on driving, which is this path and that path right there. So when you look at their output, now again, model fit, this is the interesting thing. You put this model together and you had 3 measurement models that all roughly fit well enough. When you put them into the structural model, you're not guaranteed that the structural model is going to work, going to fit well, because there's extra degrees of freedom that are going to show up now, right? In fact, we have all of a sudden 110 degrees of freedom, which is, right, if you think about it, because we have all these variables in the analysis, the covariance matrix for that thing is huge. Remember where degrees of freedom come from? It comes from the number of covariances in the covariance matrix. In the saturated model versus what you model parameters that you're trying to fit. But still, we still have an RNSEA that looks even better, 0.044. Not bad. And CFI of 0.94, a TLI of 0.92. That's awesome. Looking pretty good, huh?
So what if it's not awesome?
That's the tough part. Because, and actually, this is where... So I never started that. Let me give you a little backstory. Remember the what if it's not awesome? When I started over in that building, I never taught SEM because that's what Todd did, and then we had First Preacher, and that's what they did. And so they had like 8 forms of SEM class, but I taught everything else, right? I was only here 2 years. So it wasn't really that big of a deal. But then as I moved along, I decided, hey, I want to teach that class. So I taught it at Georgia, and I was putting together my slides, and I was talking to her about this since she sort of started her class based on something I started over there, which is the factor analysis class, and then moved into SEM with it, and we've been talking for a while. And I asked her that same question. She's like, no, it's going to fit. And I'm like, no, I have an example. It doesn't. So I looked up like David Kaplan's book. I looked up Klein's book, and none of them talk about it. So just put it together. I think Kaplan comes the closest to say, yeah, it may not be guaranteed to fit. That's all they say. So what do? You have to modify the model to make it fit somehow. But you have to modify the model as the joint model to do so. And so looking at, again, modification indices, looking at residual normalized residuals, all the things you learned before you still have to use, but now you're going to have these, you may have the potential for adding parameters that are crossing the measurement models somehow.
But you would make all those changes within this like aggregate.
That's right. And I still like the process of doing the separate measurement models to begin with, because if you think about the process of measurement, if you can separate the trait, if there are not a lot of cross-loadings and so forth, then that helps you build a better argument that each of these things you're doing well measuring those. But then when you put it together, it may be the case that the joint relationships of the variables that measure some things may also be really related to some of the other things as well. So I hope you don't get in this spot. It's hard to get resolved. Yeah.
But this is based on like already literature and the previous research.
Yeah.
So you do have some kind of, like, you're not doing this randomly. You have some
That's right.
basis of somewhat confidence.
Yeah, you're not doing this based randomly. With hers, I'm trying to think here, her stories that she's told me. The vision index is based on, these are observable variables. Like, I think there's a measure of farsightedness. So these are like optometrist level deals. These are self-reports of traffic incidents, right? And so that seems pretty tied together. These are different versions of visual attention tasks that people give. There's one called, what is it? Driver scans was hers, but there was something useful field of view. Yeah, useful field of view, and there's two different versions of what that happens, and she's always mocked that as being terrible before us, but you know, it's so point being, there's real good, I can even see a rationale for why these show up together here.
So can I ask that?
Yeah.
You'll probably get to once you're all done with all of this.
Yeah.
But like the impetus for doing this path analysis was to answer what question?
Yeah, good question. The idea was, I believe what happens is people were saying that if you're someone who's getting up in years, that you can't drive anymore, right? And so it's more to understand what process by which that happens. Is it directly that, you know, age relates to driving incidents? And if you look here, the direct effect of age predicting driving is very small. Or is it more age-related to vision, or is it more age-related to attention?
So, I guess more physical and more like contextual environment.
That's right. Or there's also processing speed, which is cognitive, and then ability to attentional focus, which is a cognitive process deal as well. So I think that was sort of the idea. Is it just we take everybody who's, you know, an octogenarian, should we just not allow them to drive, or is there something else that we should really be doing when we do a driver test to make sure that someone's able to drive?
Yeah, or do the other things not matter, and really it's just like vision that matters? Exactly.
All right, so now let's find out. This is good. Thank you for the question. I do think that's really important, and I'm so like the numbers are so shiny that I'm just like, oh, I gotta look at those. But no, really, the big picture is really important, right? So it's like this. Wow, look at that! It worked. So I think that's what's more important to me is, hey, it actually ran. So here you have all the effects. If we talk about the regression slopes, you see here now my numbers here are going to differ from what you see in that document. This document shows up under the M+ section in the website, and you can see how it runs. And that's because there are, as we've gotten more and more complex models, the differences between what Levon gives and what M+ gives is becoming a little bit more salient, a little bit more dramatic. And so I don't know which one to believe. I like Levon a lot. I'm not trying to tell you. I've looked under the hood. I feel like it's doing things well, but I don't have an actual testable hypothesis. I don't have the data in front of me to tell you which one's better. But they're different. But they're on the same order. The differences are magnitude of, like, you know, decimal places, generally speaking. They're not large. So here, let's take a look at the direct effect of each of those variables on driving. We see that as age increases, there is no direct effect of age on driving. Ta-da! So that implies that you shouldn't necessarily be taking everybody who's older's driver's licenses away. Let's talk about where are the direct effects. Visual attention does predict people's driving. So it's some type of cognitive impairment that causes visual attention As your attentional focus factor goes up 1 unit, your say driving here is the higher the driving, the more I think you have the violent. So driving is bad. The more likely you are to have all these things. So no, I don't think. I think this is driving being good. I think it's the other way around. So as attention goes up, driving ability goes up. As vision, but is vision bad? The vision factor may or may not be. So I need to look into this to get the details here. But the only thing that seems to affect driving directly is attention. What we're after. I need to get the slope right. When it comes to the indirect effects, the age and vision pathway, this age indirectly affecting driving through vision, turns out to be non-significant. The age and processing speed is also non-significant. It's the age through attention, right? And it's not necessarily, it's the standardized effects is 0.2, so it's not a large but not a small effect.
So the indirect effect of age on attention
says that
the direct and indirect effect on driving.
That's right. That means the attention is mediating the relationship between age and driving.
Oh, off the way.
That's right. So age directly does not affect driving, but attention does. But age is related to attention. The older you get, the more likely you are to have issues with attentional focus, right? So this slope right here, What's that?
So then we just teach attention.
That's if you can, or is it something that's is there some biological basis in the brain as age-related changes happen? Now, these are I think these were normal function. Actually, these are somewhat high-functioning adults. Her sample came from people living in the KC area, and she did this study at KU Medical Center. This is like 2002, 2001, something like that. And she said that just anecdotally that they were the people who were retired, but they were likely to be someone who was a formal like faculty member at the med center, or someone who's pretty well educated, right? So these are probably people who are a little bit above average cognitive ability adults. So there may be some other things that you have to control for. but I mean the result of the study though is that I think that the finding from this would be it's not just your age that matters, it's age which seems to have an impact on attention. And from what I've heard from her, it's almost less than age on attention. It's something that also applies when people tend to have, even at age, I mean, the effect of age on attention here is actually quite, it's relative, it's a standardized effect, is relatively large, 0.4, relatively speaking, but I feel like there's the big effect on that is that if you're having, if you have age-related cognitive decline, if you've got, or if you're have some type of cognitive impairment, dementia, otherwise, something along those lines, it usually shows up later in life, and so it's related to age that way. But that also might not be necessarily age-related. It might be something in biologically driven, like a genetic process or something like that as well. So, although I don't know, I'm not. This is me speculating. I'm trying to be. I do the numbers. Remember, I don't have any theories. So, but that's the thought. Does that help with the big picture?
Yeah, it's super interesting.
So it's cool. I think the cool thing about this is, I think there's a lot of cool things about SEM in general. And by the way, there's some modifications that get done in this second round. She removed one of the non-significant paths and tried to see if the model fit as well. It did fit as well, and so therefore, reported that last model, which is down here. But the cool thing is there are cool things that show up here, and one is that when you have a bunch of directly measured variables, we have a bunch of latent variables. What do you do? This analysis allows you to put them into a model simultaneously. So one of the things I've debated, I was on a students committee, and she was a student not in my department, and her advisor allowed her for her dissertation to be to do a structural equation model, which, by the way, it's your dissertation, right? So, but I understand sort of a process. And so I helped her build a structural equation model for her dissertation. And then sort of at the defense or the prelim, it was like, well, why are you doing all this complicated work? We know that you don't need to do this and blah, blah, blah. No one's going to understand it. And the first thing, it's like, well, each of your variables is measured with error. Right? And had we just added these up, had we just made a sum score out of these, which is what you'd normally do in a path analysis, like what the first example was, what happens when you put that in the analysis when you add up sum scores? The error starts to affect the slopes or the path weights, right? It has a downward, makes those go downward, but it also affects the standard error for each of your parameters. It makes it goes a lot farther down. It makes you think you have a lot more information than you really do. And so I was trying to like philosophically say, listen, and didn't have any of it. So what I want you to be able to do is to describe to your advisor or to the person that you work with, and when you get out of school, the rationale for why you do this, right? The first rationale is that if you've got latent these constructs measured with error, potentially with error, even if they're super reliable, you want to do this in this approach because the path, the regression weights that you see here, because you're able to partition the measurement error, it shows up in this variance section, right? Each variable has a residual variance. That's the measurement error, effectively. Because it's got a spot for it, it's not contaminating the model, not biasing the effects. I know we need to go. Sorry, one more thing. The other part is you can do this complex multivariate relationship in a very straightforward and quick process in this type of framework. So just be thinking about ways to describe this to people who aren't as up on it, because there is a lot of skepticism. Even now, I mean, the structural equation model has been around almost 50 years in this form, right? Actually 50 years, or close to 50 years in this form. It's been around a long time, but people are still like, why do you need to be so complicated? But just remember that it's not, and I need to remember this too. Finally, last thing, our last class is next on Thursday. I'm going to talk about what happens if you can't do all this simultaneously. There's a set of bad options to do, and what do those lead you to believe? So I'm going to show you that. And I'm debating in my head, would you guys like if I brought some lunch again, like pizza or something like that, as a celebration?
Wait, next class is the last class?
Or
Yeah.
no homework 7.
No, homework 7. I want to keep homework 7. Just kidding.
I'll be a very lenient grader on homework 7. But would you want to have? I know when we had bagels here, everybody's like, "Yeah, food. Do you want food?
Bagels.
Bagels?
No.
What would you prefer? Anybody want food?
Yes.
Who wants food? Free by me. Would you eat pizza? Pizza's easy.
Let's do it. We don't want to put you out.
No, I call someone and they bring it. It's I don't even call. I get my fingers out and I log in and it just shows up. So I'll have a couple pizzas, one that's vegetarian, and the rest that'll be some type of toppings that probably no one will uniformly agree on, but hopefully everybody will eat. All right?
Thank you.
All right. Thanks, everybody.
Can you put this article on your website?
I will do that after class. Yes, thank you very much. Last thing as you're heading out, if you haven't already done so, please do the online survey for the